Hello everybody. I would like to thank the organizers to giving me last minute chance to present here at this LISA 13 symposium my recent work, Background for Gravitational Wave Signal at LISA from Refractive Index of Solar Wind Plasma. So ground-based gravitational antennas, they have size limitation. Also they face seismic noise and they need to be equipped with vacuum technology which currently provide us with ultra high vacuum, which is 10 to 7 molecules per centimeter cubed. Because we are in laboratory there, this vacuum impurity is under pretty decent control. On the other hand, space-based gravitational wave antennas, such as LISA, are practically free of size limitation. Also, there is no seismic noise, and also vacuum is for free. Even though here we should understand that there is no perfect vacuum because there is solar wind plasma, but definitely is much better vacuum with 10 particles per centimeter cubed. However, this vacuum impurity is definitely not under our control because it is given by solar activity. And if we want to see how much it can affect LISA measurement, we should study optical properties of this solar wind plasma, and it means we should we should estimate how much is the refractive index. And for that we need to understand what is solar wind. So it has composition of electrons and protons mainly. Then there is some smaller fraction of alpha particles and even smaller fraction of heavier ions. At 1 astronomical unit from the Sun, which is the orbit of Earth and also of the proposed LISA, the average particle density is 10 particles per centimeter cubed, and because of quasi-neutrality of the plasma, the number density of electrons and protons are roughly half of that. At the scales of optical wavelengths, which is the wavelengths of the LISA's laser, the solar wind is practically a collisionless ideal plasma, and as such, it can be characterized by plasma frequencies for its components. The highest plasma frequency is that of electron component because it is inversely proportional to the mass of the particles, and the electron is like this particle. So the plasma frequency for electrons dominates the Selmayr equation for refractive index for electromagnetic wave of the frequency omega. So we end up with this formula. And for optical electromagnetic wave, we can estimate the correction because of the solar wind plasma of the refractive index from unity, and it is given by this tremendously small number, 10 to minus 21, which seems to be safely negligible unless we have some tool which can measure it, and it might be LISA. So LISA has 6 laser links operating on the wavelengths of 1064 nanometers. It has a length of its arm has average value of 2.5 million kilometers, and it is designed to reach required noise level at incredibly small level within the frequency range of interest from fraction of millihertz to fraction of hertz. This is because we want to see gravitational wave signal which should be above this prospective noise level, which is given here roughly by this dashed line. So if we want to see the effect of solar wind, we need to have data for solar wind electrons, for solar wind electron density. Our requirement for selecting the data are the following. We want to have enough high sampling frequency in order to cover the higher end of the energy of the frequency range of our interest. It means 0.1 Hertz, which is given here that we want data to be taken each 10 seconds. Then the duration of the data samples should be long enough to cover the enough periods of the lower end of the frequency range, which is 0.1 millihertz. So by selecting at least 24 hours long data samples, we cover 10 periods of the lower end frequencies. And the last point is that we want to avoid interference of the data with Earth magnetosphere. And these requirements are satisfied by the first stage of wind spacecraft, which in the years 1997 and 98 was placed for the first time in halo orbit around first Lagrange point, which is safely far from magnetosphere of the Earth. So our analysis is done by introducing effective displacement, which actually reflects the fact that the phase velocity of the laser changes with the refractive index, and it effectively produces a effective displacement of the test masses, which is given by this formula. We analyze the dimensionless quantity, which is actually only this ratio of the effective displacement with the length of the LISA's arm. And for this quantity, we calculate the linear spectral density, which is to be compared with LISA's required noise level presented before. So this is the result. Here in log in the first panel in log scale, we are showing the required LISA's noise level in black color, and every unwanted signal should lie below, and above should be only the gravitational wave signal. However, we show here that solar wind is producing signal above, and on the right side we show the same data as a ratio of the solar wind signal and the required noise level. So we can see that in this case the solar wind signal exceeds the noise level by a factor up to 6. In the first row we are showing data samples from the so-called calm solar wind conditions, and in the bottom row we are showing the results for the data from more active periods, and it goes up to factor of 10. So such analysis is applicable to any space-based interferometer of the LISA's type, meaning of the LISA's size and position in space, and also sensitivity. That effect would not be discovered before the full-scale LISA would be deployed on the orbit, because we need to have really full-scale LISA to see the signal. After all, the situation does not need to be so severe as presented here, because there might be averaging out effect. What is it? It means that actually our analysis is based on data collected from single spot in space, and there we see only time variations. It may happen that the solar wind has some variation in the perpendicular direction, to the solar wind velocity. And here in our analysis we have assumed that the typical space variation is bigger, has a bigger wavelength than is the LISA's arm. So it's this situation. So you can see that this we assume that the variation actually affects all lengths of the LISA's arm at once. If the LISA's arm happens to be parallel with solar wind, which actually whose variation travel by a speed of 500 kilometers per second from the sun, so if it happens to be parallel with this velocity, because of the length of the LISA's arm, the variation travels 5,000 seconds along the LISA's arm. So even those low frequency and variations, they travel, they actually make 5 waves along the LISA's arm, and clearly they can be averaged out. And the higher frequency, they actually are getting averaged out even more. It can happen that the spatial variation of solar wind has characteristic wavelengths which is smaller than LISA's arm. And in that case, the averaging out effect would be applicable no matter of the orientation of the LISA's arm. But this is clearly subject of future modeling of the LISA's environment, and there is a question whether we would take a risk of relying on this averaging out effect. Or we better take some countermeasures, and we are proposing here two possible solutions. First is to deploy along the LISA's laser beams enough detectors of solar wind plasma in order to know the background and to be able to subtract it from our signal. Of course, there's a big question with what accuracy we would need it to do it. It means how many detectors we should deploy. Here I just want to mention that my Institute of Experimental and Applied Physics in Prague has a good experience with measurement of cosmic particles in orbit around the Earth, and we had several projects with ESA. The second solution would be to deploy second laser system of different wavelengths on LISA. These wavelengths would be given by some chosen ratio with respect to the original laser beam, and it would allow us to subtract the two signals in this combination. And then why this combination? Because the effective solar wind displacement is proportional to square of the wavelength. So that's why this combination is free of the solar wind signal. But manipulating the data in this way, we clearly introduce some systematic bias. And again, it must be studied how big this bias would be. So let me conclude. The signal from solar wind plasma may provide a measurable background for a significant portion of the prospective gravitational wave signal of interest. This could severely constrain the scientific performance of the proposed LISA mission. Possible solutions, we are proposing two of them. Detection of solar wind background, or two laser systematic subtraction of solar wind background. Thorough modeling of the solar wind plasma environment of LISA is definitely needed. Thank you for your attention.